Hi folks, Vipin here, making a video after a long time, and my apologies for that. I've been a little busy with valuation work. But nonetheless, this is a long promised video when it comes to statistical quality control. Now, let's first understand what is the meaning of quality. Now, quality is an attribute that has been given to both tangible and intangible goods. Now, what manufacturers of both tangible and intangible goods look at would be whether or not the quality of their product is within a particular acceptable range. Okay, they look at all these different things. I've mentioned four different points here. Let's ignore the chart name for now. Um, you have the average quality, the variation, the defectives, and the defects. Okay, average quality here refers to whether the product is good or not. Okay, that's our assumption. Okay, different manufacturers define quality in different ways. So it's up to the consumer or even the manufacturer to go about giving our point of view for what quality actually means. Variation here refers to the difference. Okay, now if I were to ask you what is the variation in quality you would find between two Indian companies that manufacture cell phones, say for example between Carbon and between Micromax. So that's what you would refer to as variation. Defectives and defects. Now a lot of people get confused between these 2 points. What is the difference between defects and defectives? Okay, now, defective refers to a unit of a product. Okay, it refers to a unit of a product. The defects, on the other hand, refer to the problems of the product. That is, it refers to the problems of the product. Now, what, for example, do I mean by defectives and defects? Now, let's say that this happens to be a cell phone, and when you have a cell phone like this is one unit of the product. Now, I can say that this cell phone happens to be defective. Okay, so this cell phone is just one. Okay, this cell phone happens to be defective. So what is the reason why it is defective? I can mention the various defects. That is the various reasons why I can categorize this as a product which happens to be defective. Now, one of the defects I can say would be the quality of the screen is bad, or the touch happens to be not working. One of these in fact happens to be the defects, and hence the product in fact has become a defective product. Defects happen to be a feature, and defective is what you would refer to as a product which is in fact not working fine. Okay, now this is the basics of the theory when it comes to statistical quality control. Now I will not do the graphical part. One reason being you guys are good at graphs and you don't really need my help when it comes to the graphs. But nonetheless, I will be discussing all the different charts that I spoke about now in this particular video. Now, in order to explain the topic, let me do the first problem here. This is problem number 23. Let me double check. Is this 23 in problem in Raj Mohan book? Yes, it is problem number 23. Now I'll quickly read out the problem before we proceed. A process manufactures resistors of 1 ohm resistance. Samples of size 4 are drawn every 15 minutes and the resistances are measured. The resistances in excess of 0.99 ohms in units of 0.001 ohms are recorded below. Okay, now most of the data here is something which is not really required. Now, for example, 1 ohm resistance is not really required for you to actually calculate anything here. Samples of size 4, even that is not required here, not required for calculation at least. Drawn every 15 minutes, even that is not required. Instead, you have a long table here wherein the values in fact happen to be mentioned. Okay, wherein you have 7 samples and the values in fact have been measured of each of these samples. So what is it that you need to do in this problem? You need to calculate the X chart, and you need to calculate the values for the R chart. Now, in this particular problem, you need to consider both the cases wherein in case standards are given, that is the standards are given, and in situations where the standards are not given. Standards given and standards not given. Now, for the first bit of the problem, I will be doing the X chart. Okay, so remember this now, for the values here which I'm going to calculate are all from the X chart point of view. Okay, now let me first look at the various data that I need to gather before I start implementing the formulas. Okay, we'll leave this part of the board aside and we'll start calculating some of the pending data. Firstly, we need to calculate X. Okay, the summation X here. And now, how do you go about calculating this? You just add up the values of the sample that has been given here. Okay, now for example here, I don't know if you can see here. Yeah, I guess you can. If I go about calculating 16 plus 7 plus 4 plus 13, I'm going to arrive at the following values that you will see at the table which I'm going to write down now. So the next thing I'm going to do is 7 plus 4 plus 14 plus 19 and so on. I'm going to calculate. Okay, so summation X 38. Okay, and the next thing 44, 45, 54, 38, 36 and 46. Okay, now I calculate the total of this comes to 301. Okay, now the next thing I'm going to calculate would be the mean. Mean here is 38. Okay, remember here when you go about calculating the mean, you in fact look at the values at which you're going to add. Now you've taken 4 values. Okay, remember you've taken 4 values here. That would be, once again, I'll run you through the table. You have 16 plus 7 plus 2 plus 13. You had 38 here. Now divide 38 by 4 and you're going to get 9.5, 11, 11.25, 13.5, 9.5, 9 and 11.5. Take the total of this, it should come to 75.25. The next thing that you calculate here would be the range. If you remember the formula for range in your first PUC, it's the highest value subtracted by the lowest value. So where do I calculate the range again? I'm going to still run you through the table again. If I consider the first one here, in the first value here, the highest happens to be 16. Okay, 16 is the highest, the lowest is 2, 16 minus 2. Do the same for all the other values that you have on the table. 14, 15, 16, 7, 5, 9 and 15. Take the total of this, should come to 81. Okay, now we need few more bits of data before you actually arrive at the required answers. Firstly, so calculate X equals summation divided by K. K here would be the total number of samples that you've taken. And as per the book, the number of samples you have here would be 7. So 75.25 divided by 7 would be equal to 10.75. Okay, now do the same for R. Summation R divided by K, which will be 81 divided by 7, which will be 11.57. Okay, now the values that we want for the further calculations we've been able to arrive right away. We need 10.75 and 11.57. So let's quickly write down this in a corner. Okay, X and R. This is 10.75 and this happens to be 11.57. Now, let's calculate the X chart when it comes to standards which are given and in cases where the standards are not given. Okay, now the control limit, the lower control limit, and the upper control limit. In this case, the lower control limit is given with the formula x dash dash minus a, the standard deviation. I will get to that in some time. Plus here. The similar thing in case when the standards are not given. Okay. A2 R plus A2 R. Now, values of A and values of A2 happen to be constants. Now, how do you remember them? You just have to memorize these values. Because I've gone through the old papers, and when I saw them in the old papers, they haven't really mentioned the values in the problem. So it's better off if you go about remembering this. But remember, values of A and A2 are different for different sample values. For example, here, the sample that you've drawn here would be 4. Okay, the size of the sample here you've drawn is 4. In case the value of the sample is 5, the values of A and A2 will differ. Okay, so remember those values. The only way you can remember would be by memorizing them. So now let's go about calculating these values. Firstly, the control limit CL is a very easy value to find. In fact, CL is already given in the problem. If you remember, in the problem here, you have 11.3, which is mentioned in the problem itself. 11.3, in fact, matches this. Okay, so CL happens to be 11.3, and then the lower control limit LCL 11.3 minus A. A here is given in the book as 1.5, and the standard deviation here is already mentioned in the book. Right next to the values of X, you have standard deviation which is 3.1. Okay, so consider that 3.1. You'll be able to get the answer as 6.35. Similar thing, if you do it for the upper control limit, should get 11.3. We do arrows here. 11.3 plus 1.5 multiplied by 3.1 is equal to 15.95. Now, the same thing is what you require to do for the case where the standards are not given. Okay, in case the standards are not given. Now here, when the standards are not given, you already have one value here. That is, when it comes to the control limit here, let me just put a small division, a divider here, CL is X, that's nothing but the value that you got here, so 10.75. Okay, the next thing, the lower control limit, 10.75 minus A2, remember the value of A2, it's 0.729 multiplied by R, the value of R, sorry about that, the value of R here is 11.57. We already have 11.57, and this should give you the answer 2.315. Similarly, if you do the upper control limit, 10.75 plus 0.729. Like I said, 0.729 is a constant. It's there in the textbook. 11.57. And this should give you the value as 19.18. Okay, 19.18. So this is in fact how you would go about calculating the values for X chart. Okay. Now the similar thing is what you need to do when it comes to finding the values for the R chart. Okay. Now let's look at the R chart. The formulas are different here. So let's go through them quickly. In the R chart as well, you need to go look at cases where the standards are given and the standards are not given. So here we will call this the R chart. The standards are given and the standards are not given. Now, no further calculation you require here because you've already calculated everything. So let's look at what these values are. The formula for calculating them, D2, the standard deviation, okay. The lower control limit is defined as D1, this D2, and in cases where the standard deviation is not given, the range, D3 range, and D4. Now, in most of the cases, all you have to do here is substitute the values and multiply them accordingly, and you'll be able to get your answer. Now, again, D2 here happens to be a constant, so this is not something which would be difficult to find because it's already there in the book. Like I said, you need to memorize these values, and they may not be mentioned in the question book. So in the question paper, sorry. So the only way you can remember them would be through memorizing them. Now, as per the book, D2 here is 2.059 multiplied by the standard deviation, which is 3.1. Okay. Now here, this happens to be 0 because D1 itself is 0. So 0 multiplied by 3.1 is nothing but 0 itself. So here, the value would get would be 6.38, 6.38. And here, of course, would be 0. And again, D2 here, 4.698 multiplied by 3.1. And you end up getting the value, sorry, 3.1. You end up getting the value as 14.56. A similar thing you need to do in case the standards are not given. Now you already know the value of R. So this here in case of the lower control limit is 11.57. Okay. And then D3, again, the value of D3 happens to be 0. So 0 multiplied by 11.57 is again 0. And D4, the value of D4 is 2.282 multiplied by 11.57. 11.57. This should give you the value 26.4. Now this is how you calculate the values of the R chart. The only problem with this unit is there are too many formulae that you need to remember and the values of constants may be confusing. But like I said, the only way you can get around that would be by simply memorizing them. I'm sorry, but I've not been able to come out with any trick wherein you can actually memorize these formulas without much difficulty. Okay, now this would be the X and R charts. I will do the other two charts in a moment now. So let me go about explaining them. And now let's look at the NP chart and the C chart. This, remember, talks about the number of defectives. This talks about defects. Okay, now the formula for this is fairly easy to remember. And in this case as well, you have both standards given and cases where the standards are not given. So I wasn't really able to find time to work out a problem for C chart, but what I've noticed is when it comes to a problem for C chart, they mention the values freehand, and all you need to do is simply substitute the values and you'll be able to find the answer to it. But now let me just write down the formulas for both the the NP chart and the C chart. Okay, now we will standards given, and here not given. The first set of formulas I'm going to write would be for the NP. Okay, here CL, the lower control limit and the upper control limit. The second set would be for the C chart. Okay, C chart. And P chart. Now, here as well, CL, lower control limit and upper control limit. Now, in case the standards are given, N, P, and small p. Okay, NP minus 3 square root of P, sorry, NP and Q, and NP plus 3 square root of NP and Q. Okay, the similar thing you need to do here. Minus 3 square root of N, P and Q, and P plus 3 and NPQ. Now, why do you have the difference between the capital P and the small p? The capital P is usually used when it comes to population proportion. Small p is used when it comes to sample proportion. So that's the best way, in fact, you can remember these values. Okay. Now, sorry about that. It's small dash and small dash here. So the best way you can remember would be small p is used in case of samples and the large p is used when it comes to population. So C chart, this if you remember would be coming from the Poisson distribution. I don't know why people call it as Poisson distribution, because I find it a little ridiculous to call it as Poisson distribution. It sounds cool, but no, that's not how you would call it. And 3 square root plus the similar here. Now, like I said, due to time constraints, I'll not be able to work out all the problems when it comes to this, but I will try. So let me see how quickly I can do this. Now, for the first one that I'll be doing would be in case of an NP chart problem. And the second one that I'll be doing here would be the C chart problem. Okay, so let's start with the NP one. Now, for this problem, I have done problem number 26. Okay, 26 in the Raj Mohan book would be, yeah, in a fish nut manufacturing process, the proportion defective is 0.04 if process control is based on samples of size 150. Draw the NP chart. Now, how do you know whether you're supposed to use the capital P or the small p? The book itself, the problem itself gives you the clue. It says samples of size 150. So, and the next thing that they've mentioned before that would be the proportion defective. Proportion defective and sample together, that indicates that you're supposed to use the small p rather than the capital one. Okay, so let's see how you in fact go about finding the answer to this. So, firstly, value of p, this is problem 26. P is already mentioned, so 0.04. Okay, N, the sample size, that's given as 150. Q will not be difficult to find because when you have Q, Q is nothing but 1 minus P. Here this should be 0.96. 1 minus 0.04 should give you 0.96. Now all you need to do is substitute the values and you have your answer. Control limit here is NP. Okay, NP here, sorry, NP here is given as 150 multiplied by the proportion here that you mentioned, 0.4, which is nothing but 6. And the next thing that you have, NP minus 3 square root NPQ, and this should give you the answer minus 1.2. And when you have a negative value, you end up taking it as 0, okay, because it's not really possible to get negative defects on something. You can't really say that the number of defectives here is minus 1.2. So rather than that, you take it as 0. So the next thing that you do would be you take up the upper control limit, is NP plus 3 NPQ. This should give you the value 13.2. Now in this case, I have used the sample proportion because they mentioned it's the sample. And this is what I've arrived at. And this, in fact, should match the answers that is there in the book. Let me double check. Does it match? Problem number 26. Yeah, 6, 0, and 13.2. It does. Okay. Now let me do one more problem before I close this video. Okay. Now this would be problem number 27. Okay. In case of problem number 27, you have in a motor car manufacturing company, the chassis are being painted in a section. The number of defects on painted chassis are noted below. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and accordingly the number of defects. In this case, you mentioned defects. Okay. Defects here automatically means you use a C chart formula. Okay. Now in this case, the mean is not given. That is, the Poisson distribution value is not given. So because it's not given, I end up using these formula. It would be CL, LCL, and UCL. C minus 3 square root of C plus 3 in the square root of C. Okay, so how do you end up calculating the value of C? Firstly, if you look at the different values that have been given here, the various chassis numbers, all that being put, chassis 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The various values for this has already been mentioned. This is the chassis number, and this would be the defects in all this. I find it a little difficult to believe that a chassis has got 13 defects. This must be an American car manufacturer to make so many defects in the products that they've been making. 8, 16, 8, 4, 0, 2, and 7. I'm assuming the chassis with 0 defects is either Korean or Japanese, and the rest of it all happens to be American. So calculate this. Summation C is equal to 69. Haha, 69. And divide 69 by 10, and you have the value for C. Be 6.9. All I need to do here is, since I've found 6.9, I just need to substitute them in the different formula that you have here, and I have my answer. So CL here would be 6.9. 6.9 minus 3 square root 6.9. This gives me the value minus 0.98. Like I said, you can't have minus defects, so you take as 0. The next that you have here, lower control limit and upper control limit, 6.9 plus 3 square root of 6.9. This should give you the answer as 14.78. And let me double check if this verifies with the book, and it does. So this is in fact statistical quality control. I'm sorry I delayed this video for so long. I was a little busy, but if you want me to work out more problems in this video, do let me know. And please give your feedback when it comes to this. Thank you for your time. Have a nice day, and please don't buy American cars.